Hey, good morning, everyone. I think we can start. If there's someone else who wants to join, they can just pop in while we're busy. So welcome to this session on matroids and graphs. So we are privileged to have Professor Ann Neudauer here. She is from the United States, but with her traveling, you would believe that she does not live there. And some people do believe that she is South African. Um, so you can read in her bio where she's from and all the wonderful things she's doing. But I want to just say one thing that stands out for me about Nancy, and that is her passion for mathematics and her passion for people. And it is wonderful how she managed to bring those together. And today she is going to tell us a little bit more about how matroids and graphs link to one another. And this is specifically a point where we as graph theorists can see how we can use matroids maybe to further things in graph theory, or those who are already familiar with matroids, how graph theory can help in matroids. Eric has posted a link to a sheet that we can use throughout in the meeting chat. So if you can't see it, please just post that or tell me in the chat and we can repost it. And with that, Nancy, over to you. We are looking forward to spend the following 2 hours with you. Thank you.
Thank you, Rihanna. Thanks for the nice introduction. And also thank you and Eric for arranging this and giving me an opportunity to talk with your group and to folks across South Africa and other parts of Africa. So this is a real passion of mine for some time now, bringing matroids to a wider audience. And I wrote a expository article about this some years ago because I felt like my students had no place to kind of get started with matroids. Like there were research articles, but not kind of an introduction. And then I realized, oh, I have colleagues in many other fields who can maybe use matroids. And so trying to find a way to introduce them has been a real interest of mine. And it turns out it's just as difficult as doing research level mathematics in some ways. And so I want to talk today about matroids and their interplay with graphs, but to understand this, you kind of have to know a little bit about matroids. So the worksheet that Eric provided is just so you can play along if you want to print it out quickly and write on it or put it on your iPad or something like that. And then afterwards, we'll have a session where we can go into more depth if you can stay for the second hour. So one question we always ask is, why should you care about these things? And Gian Carlo Rota famously said, anyone who's worked with matroids has come away with this conviction that they're one of the richest and most useful ideas of our day. So maybe we'll discover why later. They were first introduced by Hassler Whitney in 1935 in a paper called On the Abstract Properties of Linear Dependence. And I put this following quote in the abstract, but it's good to think about now because this is something that I think should drive your thinking about matroids from a graph theory perspective. So Tutte said if a theorem about graphs can be expressed in terms of the edges in the circuits only. And so what does that mean? Well, that means that we're not thinking about the vertices. We don't care about vertex degree. We don't care about the vertices. We only care in the graph about the edges and the circuits. Then it probably exemplifies a more general theorem about matroids. And so I'm hoping as we go through this or after this talk, you can think about some results you know about graph theory, maybe from your own field, that only use edges and circuits. And then we can think about, oh, could we extend that to a matroid problem, or is that already known? And so what do we mean by dependence? Obviously, if we're thinking about linear algebra, we can think about linear dependence and linear independence, but we want to generalize this. And so I was always trying to think, how can we think about this sort of concretely? And in some sense, we think like, well, what does it mean to depend on something? And so then I thought, well, okay, have you ever sat in a chair that wobbled? This is a picture of a chair at my house. And I'm sure you've sat in some kind of chair that wobbled. And sometimes it's because the ground underneath it is uneven. Someone didn't do a good job laying the stones in the patio. But sometimes that's not the reason. Sometimes it's the chair itself. So imagine now your chair is sitting on a perfectly flat plane. Can it wobble? And I think the answer for everyone is yes. And so then think, have you ever sat on a three-legged chair that wobbled? This is a beautiful chair that I actually got in Cameroon on one of my visits there. And so I love it because it has this African connection too. And well, a three-legged chair never wobbles, right? And so what we can think about, why is that? Well, if you have 3 points on that plane, then wherever you put the fourth point, you have to be so precise, right? You have to make sure it's exactly on that plane. And so often you get these four-legged chairs where one is just off by a little bit, and it doesn't take much. And so in this sense, the fourth point depends on the other three. And I bring this up because later we're going to talk a little bit about the geometric aspect of this, as in points in a plane or points in space. And so thinking about the chair helps us think more abstractly about the idea of dependence. So we're going to talk about graphs, and all of you in the graph theory group know much more probably than I do about graphs. But here we just have some pictures of graphs. So we could think of this as one graph with 4 components or 4 graphs. I'll come back to these in a second, but we can also think of course, much more complicated graphs. So here we have a graph that maybe represents something like a flight map or a road network. So any of you not from graph theory who have joined, this is the type of graph we're thinking about, vertices and edges. And of course, they get much more complex than this. So this is some graphs one of my AIMS students made for an essay project modeling the spread of disease. And so the yellow vertices in the graph on the left are susceptible, and then it shows as they get infected. So back to our not so complicated graphs that we want to focus on. So what do I care about in these? Well, there's only a few things in the graph that we need to focus on right now. And these are, what is a cycle, a tree, a loop, or parallel edges. So a cycle, well, if we look at the first graph at the top, can you see my little hand?
Yeah, we see
Yeah,
the hand.
Okay, so I can point to this. So this is a cycle. And if I look at the second graph, well, this graph has several cycles. So it has a 4 cycle and some 3 cycles. The next graph has no cycles, and this is what we call a tree, a graph with no a connected graph with no cycles. And then a loop is a single edge cycle, like in this one, and parallel edges are edges connecting the same 2 vertices. A few other definitions from graph theory. Well, the degree of a vertex is the number of edges meeting at that vertex. But what we really care about in terms of matroids are the spanning trees. So a spanning tree, well, it must be first of all, it must be a subgraph of the original graph. So if I take this graph at the top, I have 2 spanning trees here. So first of all, it must be a tree, so have no cycles. And second, it must be spanning, which means it uses every vertex. And I'm only allowed to use the edges that are there. And how many edges are in each of these spanning trees? So this is our first mini exercise. We could make everyone type in the chat, but I think this is an easy counting problem. Rihanna, did you get it?
I would really truly hope that my third year students would be able to answer this if they were here in mine as well.
I hope your first year students could also answer.
Yes, I just told them this a week ago.
And so the spanning tree of a graph. So it's a connected subgraph of G, it's acyclic, and it includes every vertex of G. So those are the 3 pieces of we need. But there's a property about spanning trees that I want to hone in on here. And we just calculate how many edges, but in general, how many edges do we have? We have whatever the number of vertices is minus 1. So here I have on the left G, a graph with 5 vertices. So each spanning tree must have 4 edges. And I give 2 spanning trees here, T1 and T2. Now, the property of spanning trees that I want to think about is that I can remove this edge E from spanning tree 1. If I do this, I can always go to T2, find an edge to throw in there, and make another spanning tree. So in this case, the edge is F. Sometimes the edge might be E again. I have to throw E back in. But notice that tree 1 minus E, so this is like set minus, but I'm not writing all the set brackets because it gets messy. And so this is how we typically write it. Union with F is another spanning tree. So I can write this out a little bit more, as I might tell my students, write this a little more mathematically or formally. So I can say, look, if I have a graph and T1 and T2 are spanning trees, ease any edge of T1, then there exists some edge of F of T2 so that I get this other spanning tree. And I might ask Rihanna's third-year students, where else in your mathematical life have you ever seen this? And they'll all insist they've never seen it before until one student finally lights up and says, of course, we've seen this for vector spaces. And so in vector spaces, sometimes we call this basis exchange theorem. And so it looks almost exactly like this. If B1 and B2 are bases of a vector space. And so now I have this property in graphs and property in vector spaces that look exactly the same. And so we can say, oh, well, what else does this? What other mathematical objects do this? Or can I just generalize this? And this is exactly what a matroid is. So a matroid's an ordered pair. You have some sort of elements. We call this set of E elements and some sort of bases, whatever the bases are. The bases are the subsets of E, and then we have 2 conditions. Well, the first is no basis properly contains another basis. We know this is true for vector spaces, and this is true for spanning trees of graphs because they're always the same size. So one's not going to contain another properly. And then we have this exchange property. And so that is exactly what a matroid is. And anything that satisfies this property, these 2 properties, is a matroid. So a little bit of history of where this came from. This is according to a talk Tom Berlosky gave in Montana in 2006, sort of giving this like history of matrices. And one thing I always try to point out here is, to me, this really shows that like mathematics is trendy, and by which I don't mean fashionable, but like it goes through these trends. It kind of waxes and wanes in interest. So there's all this interest in this when it was first brought up in the 1930s. And then it was quiet for a while until like the early 60s at Waterloo. This was a big deal. And then in the late 60s at MIT, it was again a big deal. And so one question we might ask is, well, who were these Harvard Junior Fellows? And you might have heard of some of these guys. So we have Saunders MacLean, Hassler Whitney, and Garrett Birkhoff. And you might know Birkhoff from geometry and Whitney from topology and other fields, but this is when they're young. And they're all sitting around saying, hey, did you notice these different objects have these similar properties? And so these are the articles they first wrote on it. So you've already seen the Whitney article earlier, but we have some interpretations of abstract linear dependence in terms of projective geometry, and then abstract linear dependence and lattices. And so you'll see matroids come up in all these fields, but you never know who really gets the right credit for things. So maybe we should call Otakar Borufka the grandfather of matroids. I don't know if any of you have read this paper in Czech, but it was discovered in translation by Kruskal, who you might have also heard of, in 1926, which means I was, in some sense, I'm thinking we're coming up on the 90th anniversary of Matroids, but if we count Borufka's work, maybe it's the centennial next year. These are the things we should celebrate too. So I was at a conference almost exactly a year ago in Fredonia, New York, the Seaway section of the Mathematical Association of America, and giving a talk similar to this, and someone came up to me and said, "I'm so excited about your talk." And I realized he was like kind of a early giant in matroid theory. And I was like, everything I'm going to say, like this talk is for students. And he told me a little bit of this history. So when matroid theory was 30 years old, they had a conference at the National Bureau of Standards. And he was there along with Jack Edmonds and some other names we know from algorithms and graph theory, Tutte, etc. And then for the 60th anniversary, they had a conference in Seattle. And so the question is, where should we celebrate this year? I think maybe South Africa. But we're still staying tuned for the plan. All right, so back to the matroid. So we have this definition, and we have the two axioms. No basis properly contains another basis, and this basis exchange property. And then a few more just terms we can use. This set of elements, E, we sometimes call that the ground set of the matroid. And we also have the idea of an independent set. So any set of elements contained in a basis is independent. And so we certainly believe this for linear algebra. If you take a basis and then take a subset, it's going to be linearly independent. And we have this idea for a spanning tree as well, whereas if you take a subset of the edges of a spanning tree, well, it's still not going to have any cycles, right? So it's still going to be a forest in some sense. And so this idea of being independent is related to not having any cycles for a graph, at least for one matroid on a graph. And a basis, just as we expect from linear algebra, is a maximal independent set. So about some years ago, a book came out on matroids by Gordon and McNulty, and it had these 4 pictures in it. And I love these 4 pictures because it shows us, in some sense, 4 different ways we can think about a matroid. So I want to talk about at least a few of these. And of course, the first is a graph. And so now that we have this definition of a matroid and that we have this idea that, well, the bases are probably the spanning tree, let's define a matroid on a graph. And so we have what we call the cycle matroid. And so you take any graph with edge set E, then the cycle matroid is denoted M of G. And to decide what any matroid is, we simply have to know what is the ground set, or the set of elements, and what are the bases. So here the ground set is a set of edges. So and the set of bases is, as you expect from the earlier example, the set of spanning trees of the graph. So if I want to literally write down the ground set, E, I see I have E1 through E5. I have 5 edges, so there are 5 edges or 5 elements in my ground set. And now what about the bases? So we can think about the bases. Well, the first thing you might want to think is, well, how many edges will it have? And then I have to remember, okay, the spanning tree is the number of vertices minus 1. So I should have, since I have 3 vertices, I should have 2 edges in a basis. And then I can pick 2 edges and see, is this a basis? So E1, E5, for example, well, it seems to be acyclic. It seems to hit every vertex. And so, yes, this is a spanning tree of the graph. What about E1, E4? See, if this were my class, I would have a little poll set up where we could all vote. And then everyone have to click yes or no. And we say there's really a problem here. This is not a spanning tree. And I have right in the chat, not a basis. Sorry, my cursor stopped working. So not a spanning tree of the graph because, well, it had a cycle and it didn't reach every vertex. So we had two problems there. What about E3? E3 is a really important element here because not only is this not a spanning tree, it doesn't appear in any spanning tree. So we have an element of the matroid or an edge of the graph that's in no basis. And we call this a loop in the matroid. And so a loop in a graph is easy to identify, but when you get to just any matroid, how do we identify it? Well, one way is that it doesn't appear in any spanning tree ever. Oh, and Eric suggests, I'm bad at monitoring the chat, but I'm looking now. Maybe like a zero, exactly, maybe like a zero vector in a vector space, exactly. And so if I write this all out, I have the following bases. So I can find all these sets of two edges that form spanning trees of this graph. And you see how E1 and E4 act exactly the same, and we never see E3 there anywhere. So let's try again, since this is also practice along with learning about matroids. So here we have another graph, and this is the graph I showed you in the 4 pictures by Gordon and McNulty. So we have the same thing. The ground set's going to be the edges of the graph, and the bases is a set of spanning trees. And so at this point, I would ask my students, please write down the ground set. And I also think Rihanna's 3rd-year students can do this. So we have the ground set is a set of edges, although it's tempting to look at the vertices. And remember, we don't care at all about the vertices. We care about the edges, we care about the structure of spanning trees, and it's going to turn out that that means we also have to care about the cycles. And the bases. So what if I take, well, I have 4 vertices, so I know a basis is going to have 3 edges. So what about ACE? Do we think this is a spanning tree? I get a thumbs up from Rihanna, and we think yes. So that's a spanning tree of the graph, and that's one of these nice spanning trees that looks like this, like a claw. And then what about ABC? Getting some thumbs down. Not a basis, not a spanning tree of the graph. And we can say, well, okay, what is it in the graph? And notice that it's a cycle. So if I write out all the bases of this matroid on the graph, or of the spanning trees, I'm going to get these 8 spanning trees. So what about a vector matroid? Well, since I said there was a strong connection between graphs and vector spaces, let's think about what it is. So here we just need the same information. What is the ground set of the matroid and what are the bases? And the grounds, it doesn't matter if we use column vectors or row vectors. In this case, I use column vectors. So the ground set here is the set of column vectors, and then the bases are the bases. So just like we think of in linear algebra. So in other words, the linear independent set of vectors or the maximally linearly independent set of vectors? There's a question in the chat. Do you not require that the underlying set of a matroid should be finite? Yes, it must be finite. So here I have 5 vectors. So we'll say 5 is finite, but it is hard. Often we think about linear algebra in an infinite way. So we take a finite set of vectors. So there is something called an infinite matroid, and it's quite different from these matroids. And it was studied for a while, like some time ago, maybe in the 80s, early 90s, and then it was quiet for a while. And now people are studying infinite matroids again. So that's a different field, but they work quite differently. So in our case, we must have a finite set. And I should say that for the graph too, it has to be a finite graph or a finite set of edges. So I could write out the vectors, but here I labeled them A through E just so I could abbreviate them more easily. So our ground set here is a set of vectors, and then the bases. Well, since we want to play along, let's try and see what the bases are of this matroid. And maybe you can write down one or two and think about bases for this matroid. It's a little bit harder to write down the bases in this case than the spanning trees of a graph, right? The graph gives us this really nice visual way to quickly do it, at least for a small graph. And here, at least for my students, they have to think a little bit putting this together. So I know what that brings up. Why are we even looking at this? Why don't we just look at the graph? And so that's going to bring up more important questions like, can we always just look at the graph? Oh, and Eric says ACE. So what does everyone think? Is ACE a basis of the matroid? So basically, is it a basis of the vector space spanned by these set of vectors? Or is it a maximal linear independent set? So yes, it's a basis. These are the standard basis vectors. And we know from looking at this that we're going to have bases of size 3, or having found one, we know that all the bases will have size 3. What about ABC? Rihanna says no. I agree with that. That's a linearly dependent set of vectors. And if I write down all the bases or all the linearly independent sets, I'll get this set of sets, and you might check if the ones you wrote down are in here. I wrote out the vectors, but sometimes it's easier to look at least for vectors in 3 space, to look at them here. And now I can look at ABC again. So we decided that was a linearly dependent set. But what's going on here in the picture if I put them in 3 space? We note that they all lie in the YZ plane. And so you have 3 vectors here lying in just 2 space. And you may have noticed, but you might not remember the 8 bases from before, but these 2 pictures have the same ground set and the same bases, which means they're the same matroid. So since the ground set and the bases determine the matroid, now I know these represent the same matroid. So now the questions get a little harder, like, can any matroid be represented by a graph? Now I really wish I had a poll up. But you have to write down your answer, yes or no, then you can't change it because then it's like permanent. Eric says probably no. I know that Eunice knows the answer to this question. So no. it cannot be represented by a graph. What about by a collection of vectors, though? Can every matroid be represented by a collection of vectors? Victor says no. And he's right. And so if it could be, why would we worry about studying matroids, or why would I say it's an abstraction of these things? We would just study graphs or vectors, right? So we want to have a reason for studying these. So we want to say there are some objects that don't fit into these categories. And how am I going to find one of these? Well, I've only told you about matroids on graphs and matroids on vectors. So I need to go somewhere else. And if I look at these pictures, the obvious next place to go is to this geometry. The bipartite graph is a little different. You'll say that's also a graph, but in this case is representing more like a scheduling problem or a job assignment where we think of those two sets of vertices differently. And so in that case, the elements of the matroid are just going to be the vertices on the left. But we don't need that guy right now. So we do need the geometry. And now you might say, well, but now you haven't labeled the edges, you've labeled the vertices, but these are not vertices, they're points and lines now because we're in a geometry. And this book, they represented points of a geometry as just being slightly larger than vertices. So like they're literally just a little bigger. So same question. If you ask what is the matroid, we want to say what is the ground set and what are the bases. And so the ground set is the set of points. We have 5 points here. And the bases in this case, and I need to know the dimension of the geometry to answer the question of what is the basis. It's going to be the set, all sets of 3 points not on a line. So for another matroid, if I had a higher dimension matroid, it might be a set of 4 points not in a plane, etc. In this case, because I'm telling you this is dimension 2 geometry, or it all lies in a plane, any 4 points lie in a plane here. So we know all our bases will have size 3. So I have my ground set or set of elements, A, B, C, D, E, the 5 points. And now we want to find some bases of this matrix. So look for 3 points not on a line. I'll let you write some down. So any 3 points not on the same line. I have ABD in the chat. Oops. And ABD, there's 3 points not on a line, so it's great. That is a basis. And I put ACE here on the slide. So if we look at ACE, well, A and C are on one line, A and E are on one line, but all 3 are not on one line. So this is a basis, 3 points not on a line. And what about ABC? That's not good, right? This is not a basis because we have 3 points on a line. And we have not a basis in the chat from several of you. Great. So on ABC, we have 3 points on a line. So this is not independent, which means it's dependent. So we have a dependent set there. And so now we can think back to this idea of the chair. I happen to have in my house 2 3-legged chairs, which I discovered when I was trying to find an image online, and they wanted me to pay like $75 for an image. And I thought, I must have one. And I found 2. So here we go. So Here's a three-legged chair. This one's from Australia, and it's one Aboriginal chair that can easily be carried for nomadic people. And so we have this idea of here the fourth point depends on the other three, and so we have 4 points in a plane are dependent. So 4 points in a plane are dependent. In other words, the fourth leg is not needed. And you probably remember from your high school geometry, 2 points determine a line, 3 points on a line are dependent. And so that's where some of this language and ideas coming from in the geometry case. I went through that quickly, so I just went back in case anyone's still reading. So back to our geometry. And we can extend this to points in space in general. And we have our matroid for this example with the 5 points of the matroid and then the 8 bases, which are the maximal independent sets, so the sets of 3 points not on a line. And we see now we've looked at 3 of these 4 pictures, and so far all 3 of them give us the same matroid. And so I want to use this idea of geometry because we want to come back to these questions. In other words, we want to be able to look at outside of graphs and vectors. So every graph can be represented by a matrix, right? This is how we store a graph in a computer, for example. Not every matrix can be represented by a graph. So already we know that matrix is more general than graphs. And so let's start there. Let's see if maybe we can have a matroid that can be represented by a matrix, but not a graph. So can we find a matroid that can be represented by vectors, but not by a graph? And so we want to first find something in this gap here. And the most famous matroid of all satisfies this, the Fano matroid. And if you're a geometer, you probably call this the Fano plane. And so this one cannot be represented by a graph. What do we have here? Well, remember, since this is a geometry, this is the elements of the matroid, the ground set, are the points. And then this, like it said, it's a Fano plane, so it lies in the plane. So the bases are going to be 3 points not on a line. So what do I have here for lines? I have a lot of lines. So I have 6 lines that look straight to us, and then I have a 7th line that's curved. So this is a matroid with 7 points and 7 lines, 7 3-point lines. And if I want to find the basis, I find 3 points not on a line. So I can do that, but it's going to take a while because there are 28 of them. And so if I wanted to find a graph that represented the same matroid, I would just say, well, I just need a graph with 7 edges and 28 spanning trees. So just draw that with the same 28 spanning trees. Well, that's a little bit hard to comprehend, but rather I could just look at these 3 points on a line. Well, this is our dependent set. It turns out these are going to be the cycles in the graph. So I could look for a graph with, well, 7 edges and exactly these 7 cycles. And that's also going to be a problem, which is why it's not graphic. So this Fano matroid cannot be represented by a graph. It's not graphic. It can be represented by a collection of vectors. So it is what we used to call matrix, or we now call representable. And by that we mean representable over some field. And so we could spend some time and say, okay, well, what are these vectors? Can I find that collection of vectors? Can I find the collection of vectors that exactly has A, D, B being linearly dependent, but for instance, A, D, E being independent? And so that's what we're looking for, the same dependent structure. And I'll tell you what they are because it might take a while otherwise. But I do have some examples where we could work through things like that as well. This is representable by a collection of vectors only over GF2, so only over a field with 2 elements and not over any other field. So it's not represented by a graph, and it's representable by vectors only over one field. And so it's a really nice example because it's not too big either. And so when we look back at our questions, we can find something in this gap that's representable by a matrix, but not a graph. So we found this matroid, the Fano matroid, that can be represented by vectors, but not a graph. And then what about if we stretch to our geometry to look for a matroid that cannot be represented by a graph nor a matrix? So not graphic, not matrix. I guess the question is, do you think this is possible? Well, it should be possible because I already said the answer to the first 2 questions was no. And this is our friend, the Vamush matroid, which is not representable by a collection of vectors over any field. And so what do we have here? Well, this matroid has 8 points, the 8 points you see in red. And then it has a bunch of 4-point planes. So remember, 4 points on a plane are dependent, 4 points not on a plane are independent, and it has no 3-point lines. So that Fano matroid had 3-point lines everywhere, and this one has none. And so it's really nice, compact representation of a matroid that cannot be represented by a collection of vectors over any field, and then of course not by a graph either, because if it can be by a graph, it can be by a matrix. And so this is one reason we care about going to matroids, is because we have this idea of going more general. And so every graph can be represented by a matrix. Not every matrix can be represented by a graph. So we have this matrix structure, which is more general. And then we can go outside of graphs and matrices into a geometry, and that's more general. And matroids are these objects we study in order to understand dependence properties of discrete points in space. I'll just comment here that for a long time we studied space, and I mean, like, by a long time I mean for millennia, we've studied space by studying continuous space, even when we had discrete points in space, not because it was continuous, but because we didn't have the tools to approach this discrete structure. And as computers become more advanced and as discrete mathematics becomes more advanced, we have more tools to approach this. So for some of these problems, it might be the right way to look at them. And then the other benefit of matrices is that by studying this abstract version of phenomena that occur in different realms of mathematics, we can learn something about all these realms simultaneously. So I mentioned that we could take a graph theory problem that talks only about the edges and cycles and extend it to matroids, but we can also take a matroid result and bring it to graph theory or to other fields of discrete mathematics and mathematics in general. And so I always tell my students, when you learn new mathematics, think, what is it good for? And so we have several ways to look at this. Matroids are generalization of independent systems. They unify several areas of discrete math. And there's a large variety of equivalent axiom systems that account for versatility and applicability. So I only told you one. I told you how to define a matroid in terms of the bases, because I think it's the most natural looking from a graph and a vector space from the spanning trees and the bases. But often they're introduced first by looking at the independent sets instead of the maximal independent sets or the bases. Sometimes they're introduced by looking at the circuits of the matroid, which would be like looking at the cycles of the graph, or the minimal dependent sets of the vector space. Sometimes they're introduced by looking at the hyperplanes or the flats or all different structures in a matroid. And they're really useful in many areas, and depending on what you're looking at, for instance, they're used in industrial engineering and statics, and then they might look at something completely different from how we would look from a graph theory perspective. So the examples include networks, matrices, as you saw, configurations of points, arrangements of hyperplanes and geometric lattices, and results from one field can be used to prove theorems in another. And then lots of applications. We have algebraic geometry, knot theory, braid theory, network reliability, von Neumann algebras, electrical engineering. And then, as I said in my abstract, they're essential in combinatorial optimization. So what do I mean by this? Well, I mean this in a very, very direct way. So the greedy algorithm guarantees an optimal solution for a problem if and only if the underlying structure is actually a matroid. And if anyone doesn't know what a greedy algorithm is, it seeks a global solution by making locally optimal choices. And so if we're wondering whether or not the greedy algorithm is going to work, well, it's the equivalent to asking the question, is this a matroid? It's a characterization of the greedy algorithm. I was talking about matroid theory being trendy, like lots of mathematics can be. And since 1998, there's been a huge resurgence in activity, and especially to seek a structure theorem for matroids, analogous to the recent one from graphs. So there was the graph miners project of Robertson and Seymour and Chudnovsky, et cetera. And so there's a matroid miners project, which asks about matroids representable over various fields. And that work has been very slow. There's a new result about every 20 years. And so in 2011, James Oxley, who wrote probably the graduate text in matroids, said matroids have emerged from their adolescence, which means to me a lot of the easy problems are gone. These are just a few things I've worked on in matroids. I started out by building bridges between the graph theoretic and set theoretic representations of bicircular matroids and transversal matroids. I did some problems on enumeration, comparing two different matroids on a graph, one called the bicircular matroid and the other cycle matroid. Worked on some circuit spectrum problems, fixing number of matroids, which some of you may have heard me talk about here before, matroids on groups, co-circuit cover problems, connections between block designs and matroids. And then, as I mentioned, bringing matroids to a wider audience. So I wrote a paper called Matroids You Have Known, and now a book that's coming out in, when it's finished soon, I hope, Matroids for the Working Mathematician. And I've also worked on matroids on near vector spaces. It's a picture of some of my students. Someone asked about my course. So I think Eric, and I taught a course called Designs, Matroids, and Graphs. And I've also taught a course called Graphs, Matroids, and Designs, just different emphases. I always like to show this picture because it shows what a great setting Ames has. So this was climbing the peak with some of my students learning about the projective geometries in the Fano plane. And I haven't just taught at Ames South Africa, but in Tanzania. These are not my students. So this is when we had Ames, Tanzania, this was a nice advantage to going there. And in Ghana, eating with some of the students. These are two of my students from the US who came here for a workshop for African women in discrete mathematics. This is where I first met Rihanna and Karen and many other of you. And of course, and maybe Eunice as well. I know Eunice was there, but I don't know if we had met before that. So this was a really fantastic turning point for me to learn more about mathematics in South Africa. And here are the conference participants. Oh, you were a student there. That's awesome. All right, see in the chat. So we have these 4 pictures we looked at, and we can think about how some of this stuff fits together. Like we see that some matroids are graphic or representable by a graph. And these all lie inside the ones that are representable over a field. So that means we have a vector matroid, or we can represent these by a matrix. So the Fano matroid lies out here, not graphic, but out here. Transversal matroids are another important set of representable matroids I've done a lot of work on. And then Famos lies out here with some other friends, but I really like this quote. At times I gaze at the future and contemplate a mathematics in which there's no graph theory, but this mood does not last since I'm naturally optimistic. And we have a glorious resurrection in the form of matroid theory. This is written by Blanche Descartes, who is not a person, but it's a collaborative pseudonym used by these mathematicians. And I said this quote at the beginning, but coming back to Tutte, you might see a little bit now that if you can express a theorem in terms of only the edges and circuits of a graph, can we extend that more generally to a theorem about matroids? So I want to think about like problems we can reframe like this, but I want to also give you an example of one that I did. So James Oxley asked some time ago, does every 2 connected matroid M have a collection of some number of co-circuits such that every element's in at least 2 of them? So this is an example he had of a problem that only talked about cycles and edges in some sense. If we reframe this as a graph theory problem, I haven't defined co-circuits, but it's a circuit in the dual. And CM is the size of the largest circuit in the matroid. And so this is a matroid extension of this famous graph theoretic bound of Erdős and Galai. And we solved this problem not for all matroids, but for bicircular matroids. So what we showed was for each bicircular matroid, we can find a co-circuit cover of size at most the circumference that contains every edge at least twice. So it's taking this graph theoretic bound, extending it to matroids, and then, well, for us solving it for one class of matroids. It had already been solved for another class, which are the binary matroids, or matroids representable over a graph. So this is a second type of matroid on a graph. And just another plug for the upcoming book. That's all I want to tell you right now.
Thank you, Nancy. I'll start with the first question, if I may. So so I could probably Google this. I did quickly, and then I decided I'll rather ask you. Better answer, and I have to read too much if I Google this. So graphs, the fact that you only connect 2 edges or 2 vertices with an edge, maybe the restriction that is bothersome. So what is the connection between matroids in hypergraphs, where you define your edges as a set of vertices and not necessarily just 2 points?
Maybe Eunice can answer that question. But I'm going to go back to this picture because, I think what you're asking is represented here, where say like the ones that are connected by only 2 edges kind of fall into here or into the graphic part. And then if you extend beyond that, it must fall somewhere out here. Oh, and Zurab says that a hypergraph does not have any axioms.
Yeah, a hypergraph is just a set with a bunch of subsets with no conditions.
So a transversal matrix or transversal is a set with a bunch of subsets, and then some, we can satisfy the conditions of a matroid by looking at the partial transversals. And so I wonder if that's also true for hypergraphs. So do you want me to show you an example, Brianna?
Nancy, and catch the.
Sorry?
Can you just repeat that part about the transversals again? I didn't catch the first part.
So for to define a transversal matroid, we have a set, and then I think it's easier if I show you an example, maybe. Okay, so here's the 4th graph in the McNulty and Gordon examples. And so I've just like listed some of my friends here as representing these vertices, and then listed on the right some different jobs I need done on my house. Like say I'm building a house and I need someone to do the plumbing and someone to do the tiling and painting and someone to do the electrical. And then an edge represents which jobs they can do. So Abel can do tiling and painting, but nothing else. And Bertrand can do these 2. And so what I'm looking for is having all the jobs on the right covered. And so I'm looking for what we call a matching, or in transversal theory, we call this a transversal. Bye, Eunice. She just has to leave. So if so we want to find a set of 3 people who can cover all 3 jobs. And that's a transversal of this graph. And it's going to be the basis of a matroid. So a transversal matroid has as a ground set the set of vertices on the left part of the bipartite graph, or as Zurab said, for like a hypergraph, you can have this just a set of elements, right? And then the bases are the set of matchings. And so for a transversal matroid, we would have to have a collection of sets on the right, like set X has all the edges connected to it, so B and C, and set Y has all 5, set Z has just these 2, D and E. And so I'm not sure for a hypergraph, with a hypergraph, if you have this structure, but if so, we can find the system of distinct representatives or transversals and then build the matroid that way, because that's what the bases are. Does that make sense, Brianna? So in this case, the ground set is A through E, and the bases are all the matchings or all the transversals of that set. Eric has a question.
Yeah, can I ask now? Yeah, thank you very much, for a nice talk. It's maybe the first Matroid talk that I feel like I'm able to follow a big part of it. So it's more comment, but some part of it will be a question. I wonder if the bicircular Matroid is what I think they are, where the bases are spanning subgraph that has one cycle but no cycle. Yeah, that's one thing. And then secondly, does it exist in Metroid also the version where, for example, instead of allowing a cycle, not allowing a cycle, maybe we don't allow a complete graph. So, for example, spanning subgraph that doesn't have complete graph in it. Yeah, that's gonna be hard because one vertex is a complete graph, one edge is, but something like not allowing complete graph with bigger than two vertices. I don't know if any of this makes sense.
So the first question, a bicircular matroid, yes, in that case, the bases are they're spanning sets with exactly one cycle. So it can be like a tree plus an edge, or it can be, yeah, but spanning sets with exactly one cycle. And so maximal spanning sets with one cycle, I'll say. And then and one way to think of the bicircular matroid is in the cycle matroid, the circuits of the matroid, so the minimal dependent sets are cycles in the graph. In the bicircular matroid, you have two cycles. And so you can have two cycles like connected at a vertex, connected by a path, or you can have some subdivision of a theta graph. And then the idea of having, what did you say about having no bases that are complete graphs?
Yeah. That probably wasn't so clear. So what I was thinking is when we define the circular matroid, when you make your basis, you take a spanning subgraph that doesn't contain cycle. So I was wondering if we can also think of something of like we're gonna call it complete matroid, but that's a bad name, where we instead of not allowing a cycle in a basis, we don't allow a big complete graph. A complete graph is where every edge is connected. So for example, it's gonna be no triangle because that's a complete graph with three vertices, and then no K4, which is a complete graph, something like that. But yeah, maybe that need a little bit of thinking. I'm just trying to push the graph theory part so that we answer yes finally to that a question that does all Metroid can be represented in a graph, since there is so many ways. Maybe that's one way to have like K3 or KN Metroid, where we don't the only complete graph we allow is a vertex and an edge, but in none of those. And it could be not interesting. I'm not sure. I'm just thinking.
Yeah.
Sorry, Eric, what is
obviously
it?
for the cycle matroid that I define, this wouldn't work because spanning trees won't be complete graphs beyond K2. But like, would it be another matroid is a question. I
Sorry,
think
Eric,
it would probably fail the basis exchange axiom.
Yeah, I mean that's of course a question. Will it satisfy basis exchange axiom, or I don't know. Yeah. But,
sorry, Eric, I
it's
didn't
quite
understand.
interesting.
What is the definition of independence that you gave?
You asking me?
Yes.
Yeah. So suppose you have a graph, okay, and then we define basis first, not a dependent set. We call basis instead of what Nancy presenting as a basis will be a sort of a spanning subtree. We call basis a spanning subgraph that has no complete graph of order bigger than We can't put 2 in and 1 in, otherwise we're not gonna get a graph. But yeah, so no K3, no K4, and so on and so on. Yeah. So as long as you have a spanning, will it still satisfy the exchange theorem? I'm not sure. I haven't thought about it. Yeah.
I think
Or is it clear
I
it
think
doesn't?
that, I think not. I think it won't satisfy exchange, but yeah, we'd have to try that. It's a good idea.
Yeah. Anyway.
Nancy, can I also ask a question?
Of course.
Does the following example come up? You have a pose set, and you call a set independent when down sets of 2 elements in the set, they never overlap.
Yeah, I haven't worked too much on matrices on lattices, but there's lots of results on this in lattice path matroids and things like this. So I have to think about that, but I think so.
Yeah,
I think
it might be a bit
think that
boring
would
example.
satisfy.
Because you might only have one basis. By the way, can you have matroids? Of course, it's very uninteresting, but perhaps. But you have matroids with just one basis, right? It's possible to have that or
Yep,
not.
yep. You can have matroids with just one basis. But yeah, maybe less interesting.
Yeah.
Rihanna, did I answer your question somewhat about transversal matroids, even though you asked about hypergraphs to begin with?
So I understood this part, but you said something when you explained it, and I didn't get that part. But I don't know how this fits with what you said then. But it is okay. Don't worry too much, because I doubt that you can remember exactly what you said 10 minutes ago.
So yeah, what I said was so we have this ground set E here in this example. And if instead of drawing this bipartite graph for you, if I had just written the 3 sets representing X, Y, and Z. So X would just be the set BC, Y would be the set of all 5 elements, and Z would be the set DE. I could then ask you, just with those 3 sets, can you find all the maximal partial transversals? And so I was wondering if like the hypergraph is looking at this similarly, like if we would take each vertex of the hypergraph and look at all the edges adjacent to it, and if it was somehow, so that's what we call a presentation of the transversal matroid. But the hypergraph, maybe there's some structure like that we can look at within it. I haven't really worked with hypergraphs much in a long time, so that's why I'm like trying to remember. Victor asked if there's any connection between the matroid obtained from a graph and its line graph.
Say again, is it a question?
Yes, that's a question.
Nice.
But it takes us away from the hypergraph question. Were you going to say something about hypergraphs, Rihanna?
That's just the vertices and its neighborhoods.
Sorry, Rihanna, we couldn't. Well, at least I couldn't hear you. I think you said it silently, and the voice didn't come through.
Yeah, you were
what
breaking
you
up a
said.
little.
I said you can express a hypergraph in a bipartite graph like this as well. So I think we can kind of answer the same kind of questions that Nancy suggested. That would be my guess, but I'm not sure. If we have to step away from hypergraphs, I didn't hear the question about line graphs, Nancy.
Oh, that's okay. I'll come back to it in a second. Yeah, That's what I was thinking. We can represent the hypergraph like this. And so then maybe we look at the transversal matroid on a hypergraph, and that's a structure we can look at. So even though like the hypergraph itself maybe doesn't have its own axiom system, it does have this structure of incidents and things like that, which is maybe not exactly like a graph. But what I had earlier said, let me go to that Venn diagram, is I thought hypergraphs might fall in here, like under transversal, but only maybe intersect graphic when they're exactly also a graph.
Yeah, I would actually guess that it's going to be much larger than that.
You think it's much larger than transversal?
And do that, but not so not immediately, but I would feel that we can maybe find something that would be the one. But I'm not sure.
We should look at what's been done with hypergraphs and matroids.
There's been some stuff on that. There's a book about it.
Are you talking about the representation of matroids in a different way? Because the matroid itself is a hypergraph. Are you talking about viewing hypergraph as an abstraction of a graph and trying to get a matroid out of it that's similar to how we get a matroid out of a graph? So that
I was thinking, synopsis.
Okay.
How would
could I ask a question, Nancy?
Just a second, there's one in the chat that
Oh,
I'll
yeah,
come back
yes.
to first, and then we'll come to user. It's asked, is there any connection between the matroid obtained from a graph and its line graph? So I'm not sure the answer to this question. I can say that there's a really strong connection between if you have a planar graph and look at its dual, or if you look at the matroid on a graph and look at the dual of that matroid, there's a really strong connection there where instead of taking the dual of the matroid, you could have just taken the cycle matroid on the dual graph and you get to the same place. And so there's a lot going on between the matroid and the dual of a graph. And of course, we define the dual of a graph only if it's planar, but we don't need that for matroids. So if we take a matroid on any graph, we can define the dual. And so that's also really strong, but I'm not sure about the line graph. I imagine someone has looked at this, but I haven't read about it, so we can look that up. That's a great question.
Azura, you had a question?
Is it possible to, I mean, is there an interesting notion of a sub-matroid? And more specifically, I'm wondering if it's possible to define independence inside a matroid so you get a matroid of a matroid.
I mean, you can restrict a matroid to only a certain set of its elements. You can delete elements, you can contract elements. So you can do matroid operations like this. So I suppose in a sub-matroid, I would just restrict to only a subset of the elements I want to look at. And can you have a matroid on a matroid? I'm thinking what this would be. So is that what you mean by a submatroid, like a restriction of the collection of elements? Yeah, we can.
Yeah, sure. Yeah.
Yeah, we can definitely do that.
Yeah, no, my question was more if you already encountered people doing that. Especially the matroid of a matroid, that part.
I haven't encountered that, but myself, but it doesn't mean no one's doing it. But I wonder where that gets us to. Eric, did you have a question?
Yeah, it's not a question, but I wanted to comment a little bit about Victor's question. So, I mean, some fact is a line graph, a cycle will stay a cycle, but just shorter. And a line graph will have more cycle than the original graph. And yeah, so if we stick on, if we stay with what was it, a circular matroid, then there might be something we can say about the basis that uh, uh, yeah, I was about to say maybe it's getting harder to find basis because there is a lot of cycle. Or maybe that also make it more because the spanning subgraph subtree that we're looking for does not have to be induced, so there will be more bases probably. Yeah, just some comment. I don't know if that's useful for Victor, but yeah, that's what happened as you go from a graph to a line graph. Cycle will stay cycle, it just gets shorter, and so on.
Yeah, that's great. Thank you. I'm sure you noticed also that the title of the book is a nod to Saunders MacLean. Eric, do you want to share the document with the problems? Or I mean, these questions are
No
good.
problem. I can do
This
that. I
document.
can do that. Just 1 second, and it will be there. Second document. Yeah, I've posted now the second document. Let me double check if it's really the one. Yeah.
So Rihanna had suggested a series of problems. Sorry, someone just came in. Similar to a tutorial or something. So I put together some problems that we could possibly just look at if you wanted to understand a few more of the structures of a matroid beyond just the bases. And so Eric has shared that, and I can also post it here if I stop sharing this one.
Yeah, maybe sharing from your side, then we can focus on one problem at a time together.
Yes, I'll share it from my side. Oh, here it is. Okay. Yes,
Sorry, I need to go soon. So before you move to the problem session, maybe I could just make a comment. So you said at some point that all the easy questions have already been answered. Maybe one way of finding new easy questions is to find new ways of constructing matroids. And
yeah.
yeah.
I'm definitely open to ideas for sure.
So it's in the direction of Eric was saying, I guess. So it could be that in whatever area a person is working in, maybe the whatever special concepts they're exploring there, maybe that there is some sort of new kind of independence that emerges there. One could try to use that as a new way of constructing matroids. That could be maybe a source of further relatively easier problems to work on.
Well, that's exactly what we need. We need some lower hanging fruit because, you know, people are working on these very, like I said, they work on these problems of representability. So this first paper in 1935 essentially asked which matroids are representable over various finite fields. And so from 1935, the first question was answered about GF2 in 1958, so 23 years later. And then the next question for GF3 wasn't answered till 1979. So obviously this is very slow moving, and those were the two easy ones. And so, yeah, that question is certainly hard. And so I like this idea. And it's really, I appreciate you coming, Zora, because it's helpful to have someone not from graph theory. Because obviously when they started working on this, everyone looked at it from a graph theory perspective. So from graph theory, we either want to say like, well, what are some things we've worked on recently that you could phrase in terms of only the edges and cycles in this way? Or, as you say, like, define it somewhere else. And that's been helped with some of my work with, say, Karen, because we were able to look at matrices on near vector spaces, which no one had looked at. And so it's not quite a vector space. And what happens? Does the matroid fall apart or does it work? And things like that.
So in a different work of one of my PhD students with Sophie Marquez, we show that we explain that a near vector space is actually a special kind of a module over a monoid. And one can maybe try to look into matroids over arbitrary modules over monoids, not just near vector spaces.
Sure.
Also talking about not coming from graph theory, I looked on the internet. There are already some papers about the categories of matroids. Of various categories of matrices. So that's another link, perhaps specifically with my field. But yeah, it was very, very interesting talk. Thank you very much. Very, very exciting topic. And I hope to engage more with you and everyone else. I told you about this focus area that we have on mathematical structures. And I think a topic like this really fits nicely in such a focus area, because of its potential of bringing different structures together. That's actually our goal, eventual goal in this focus area, is to bring the different mathematical structures together. And I think this topic fits nicely into that.
That is awesome. I hope with bringing this work to other mathematicians, that it does touch on many fields and probably more than we know so far.
Okay, so I'll have to go, unfortunately, but this is being recorded and it will be placed on the YouTube channel of NEFAX. But somebody should maybe just make sure that the recording will stop at the appropriate moment. Whenever you don't want things to be recorded, then you can stop the recording. Then we will send the recording to NEFAX. Bye, everybody. Thank you again.
Everyone.
Bye.